So we said that the fMRI signal is a mixture of some signal of interest, you know, some part of the brain having a stronger signal during a mental activity and a weaker signal in the absence of that mental activity, plus some amount of noise. Now, what are the principal sources of noise in fMRI? Well, a number of them. A number of these noise sources are related to the hardware and the way in which we acquire data. For example, system noise, you know, just the measuring equipment has some variance to it. The machine in of itself, although it does create very homogeneous magnetic fields, they're not perfectly homogeneous. And that creates noise. Another source of noise, and we'll discuss that shortly, slice timing acquisition. The fact that the way in which we acquire data injects some potential noise in there, and we need to fix it. So one source is related to just hardware and the way in which we implement MRI sequences. A second big source of noise is subject related. The fact that you put a subject inside the MRI machine adds noise to the data. For example, obviously participants have spontaneous oscillatory physiological noise. You know, heartbeat, respiration are fairly consistent sources of noise in our data. Field inhomogeneities. So for example, if you put somebody's head inside a smooth magnetic field, because of the differences in magnetization in tissues in your head, you'll remember we discussed this in our second lecture. Different parts of the head, different tissues will magnetize to a different extent and will create areas of inhomogeneities. For example, you know well that at the boundary between the sinus and the brain, there's a large area of inhomogeneity. So just by virtue of putting a participant inside the magnetic field of an MRI, you're injecting noise in the measurements. Then, and perhaps the biggest culprit of problems in bold fMRI data, head motion. It's just very hard to stay perfectly still for, let's say, 5–10 minutes. So participants will move, and that will create a lot of problems, which we will discuss a few slides down. Finally, there might also be just some psychological sources of noise. For example, alertness or learning. Your participant might, you know, become more and more alert, or maybe might fall asleep or might sort of doze off a little bit. That will put noise and change the system, and therefore change the measures that we are acquiring. The same is true for learning. Maybe your participant learns throughout the experiment, and that might change a little bit what's happening. Or you might imagine that your participant at the beginning is a little nervous about being in the MRI machine, so has a heightened heartbeat that increases the CBF, the cerebral blood flow, and therefore the signal, as you know, if the CBF is increased, that the change between on and off is a little smaller. Then, as the experiment progresses, your participant maybe calms down, heartbeat decreases, maybe CBF overall decreases a little bit, and now you're getting a stronger signal. So there are all these sources of noise in fMRI that we need to try to address. And that is what preprocessing is for. Finally, the last source of noise is white noise, just random noise. And this, everybody likes white noise because it's easy to address. If you just repeat the same task multiple times and give participants the same task multiple times, that will help you eliminate white noise. The other sources of noise, however, are not white, and those we have to somehow try to fix. So how do we correct for noise in fMRI? Well, two families of strategies. First, before you ever start acquiring data, you want to set yourself up for success, or maximize your SNR, as we say. For example, you might want to choose good technology. You want to have, if you have a choice between a 0.5 Tesla and a 3 Tesla, you want the 3 Tesla, because you know it gives a stronger M0. You might want to choose the appropriate coil for what you're trying to do, either a full head coil or a surface coil. Then you want to choose good sequences. You want to make sure that your TE, your echo time, is set appropriately. And I'll give you an example of this in just a moment. You want to pick a good voxel size for the structures, the brain structures that you're interested in. If you're interested in something very tiny, you probably want very small voxels. On the other hand, if you're interested in large parts of cortex, maybe it's perfectly fine to acquire slightly larger voxels. And of course, you also want to know that the scanner is fine and doesn't have any issues, because that too can be an important source of noise that in fact you might be unable to fix. So the first way in which we address noise is simply we set ourselves up for success by ensuring that we make the right choices beforehand. Then, once we have acquired the data, so once we have our data in hand, really what we want to do is the so-called detect and correct approach. So you really want to look at your data to ensure it's okay, just quality check, and you really want to be able to do that. But then really the bulk of it is so-called pre-processing. And there are different ways of doing pre-processing. We will focus on the standard way of doing pre-processing, which will be the topic of today and the next lesson. And finally, nothing wrong with looking at your data again, just to make sure the pre-processing didn't insert anything strange in your data accidentally. So let me give you a couple examples of the maximizing SNR before you start. As I said, choosing the right parameters is particularly important. Here I'm giving you an example with TE. You'll remember from the biophysics of BOLD that TE plays a crucial role. If you wait too long, protons will dephase, and they will dephase so much that you will get no signal, right? So the image will look black. As you know, some parts of the brain, because they're nearby boundaries, for example, the sinus and just above the ear canals, are particularly susceptible to protons dephasing a little faster than in other parts of the brain where there aren't boundaries. So on the left, you see an image that has a short TE, which means the picture, the echo, is captured shortly after you stop the radio frequency pulse. Who knows? Let's say 25 milliseconds. On the right side, instead, I'm showing an image that maybe waited 50 milliseconds to capture before capturing the echo, or as I say, snapping a picture. And what you're seeing here is that there are certain parts of the brain, those nearby big boundaries. So right here, just above the sinus, and on both sides here above the ear canal, where there's entirely no signal. Now, to be clear, there is brain here and there is brain here. It's just because those protons are nearby a boundary, they dephase faster than everybody else. So the brain where there are no boundaries, you can still see it. There still is signal. But the protons nearby boundaries have already dephased too much. By the time you take a picture, there's nothing left to see. It's all black. So you want to make sure that you set the TE appropriate for your experiment of interest. If you're doing an experiment, for example, you're doing social neuroscience, or you're doing a language receptive experiment, with social neuroscience often implicating these type of medial frontal regions in their tasks, and language often eliciting activity in the bottom part of the temporal cortex, exactly here where there's this signal dropout. If you care about those regions, you need to make sure that you select a TE that will allow you to see activity in those regions. So you will want a slightly shorter TE. So you want to make sure that you pick the right parameters for your experiment of interest. Now, the other point that I was making earlier, you want to make sure the scanner is okay, because sometimes little blips in the scanner will cause massive problems to your data that you cannot fix. What you're seeing here is exactly that. See these big stripes? They're due to a problem with the machinery. They're not supposed to be there. However, they will completely ruin your data. So you want to make sure beforehand that the scanner is fine and doesn't have any problem. Because if this is in your data, you're gonna ditch this data. You can't use it. And it's very hard to fix after the fact. Finally, sometimes things like this might happen. I don't know exactly what was the cause of this warping, but you can see this warping here probably due either to old style fillings, so nothing that they would do today, but all kinds of fillings, or some kind of orthodontic prosthetic inside the participant's mouth. And although it looks like it's only warping sort of the part of the head, it most likely is also affecting the brain. So you're probably not getting good data from this anyways. So before you ever acquire data, you want to make sure that the data you're acquiring, has the best chance of being good as possible. Now, once you're done with that, the bulk of the time, once you have fMRI data, you will spend pre-processing the data. And so what I want to do for the rest of this lecture and the next one is actually to cover what are the principal steps of pre-processing.